All right, hi everybody. Welcome to Unit 2, Presentation 4. And we'll be talking a lot about graphing this week, right? So we'll be looking at graphing through the lens of acceleration. So it's really important that in this set of notes, that anytime that I show any kind of graph or any kind of drawing, you need to screenshot those and include that into your digital notebook. All right, here we go. Okay, so a little bit of vocabulary. This week we're going to be talking about acceleration. Basically, when an object accelerates, it does one of these three things, okay, or at least it can do one of these three things. When we always think about acceleration, right, when you hear it, you usually think of, oh, something is speeding up. That's true. However, something can also accelerate if something is slowing down, right? And you'll hear that as something maybe sometimes called negative acceleration, but it's still acceleration. So something is accelerating even if it slows down, right? Because it's changing speeds. And that's what acceleration is. Anytime there's changing speeds. And then the other one is if an object changes directions, right? So if it was moving north and all of a sudden it moved east, even if it didn't speed up or slow down, it still had a change in acceleration. So again, acceleration is if an object speeds up, if it slows down, or if it changes direction, right? And then the other thing that we're going to be talking about in this set of notes is slope. And that's basically the steepness of a line on a graph, right? So if something is more steep, that means that it is more vertical, while something that is less steep is going to be more horizontal. So every graph that you make tells a story, right? So the graphs that we'll be making are distance versus time graphs. And every one of those graphs tells a story about how that object is moving, right? Whether it's speeding up or if it's slowing down or is it moving at a constant speed. So in this week's lesson, we're going to be looking at graphs and being able to identify just by looking at its slope, right, how the steepness of a line, and we're going to explain what happened to the motion of an object. Right, so in the very first distance versus time graph that we're going to be looking at is objects that are moving at a constant speed. Basically what we mean is that there's no acceleration happening whatsoever, right? The object is not speeding up, it's not slowing down, it's not changing directions. It's staying at the exact same speed the entire time, right? So if you look at the graphs, and I've given you three separate graphs here, you'll notice even though they're going in different directions, you'll notice that every single graph is a straight line. And that's exactly what a linear graph means, right? A linear graph means straight line. And what you'll notice is that the slope is completely consistent, right? The slope, the steepness of the line never changes from one dot to the next dot. It's always straight, straight, straight. Okay, so that's what I mean by a straight line or slope stays constant. So if you look at all three of these graphs, you'll see that they're completely straight. So anytime you have a graph that is completely straight all the way through, the story of that object is that it is not accelerating. It's staying at the same speed. Okay, so now let's look at a distance versus time graph for an object that is speeding up, right? This is still, now we're talking about something that is accelerating. Okay, so if you look at it, what we're going to look now is it's going to look different from the graph that we just saw, right? In the constant speed, it was a straight line. What you'll notice with an object speeding up is you'll see that the graph gradually gets more and more vertical, right? We call this a nonlinear graph. What a nonlinear graph means is that there's a curve or there's a bend in the line, right? Before, we didn't see a bend in the line, right? It stayed consistent. Now what we're talking about is, and I circled it here, is from point to point, what you'll notice is that there is a slight curve that goes more vertical. And what that means is the slope, right, the steepness of the line is getting more and more. It's increasing. So if an object is speeding up the entire time, what you're going to notice is the trend that the line gets steeper and steeper and steeper every single time you see one dot to the next dot to the next dot. So that's what we're looking for when we're looking for an object speeding up, right? If it's accelerating in the sense of speeding up, we're looking for, is there a bend in the line where it makes that dot to the next dot a little bit steeper. Okay, so now let's look at an object that's going to be slowing down the entire time. Okay, remember, this is still accelerating. It's just accelerating where the object is slowing down. All right, so now if you look at the graph, you'll now see that the shape is a little bit different, all right, from the other one. Now again, because it is changing, its motion is getting slower, or it's changing speeds, the graph is going to be nonlinear, right? What that means is, right, there's a bend in the line. So clearly this is not a straight line. It's bending. You'll see that it's bending in a totally different direction than, say, when it was speeding up, right? Speeding up, the line was getting more vertical. So now here, you'll notice that the line is getting more horizontal, right? It's not going down. I don't want you to think down. That's not a right word, because down means that it would be going this way, right? But what you'll notice is it's starting to flatten out, right? And when it flattens out, what we're saying is the slope decreases, because the line is getting less and less steep as you're going through it. And you'll notice that it does that the entire trend here. So to look at it and kind of like zoom in a little bit onto one part, you'll notice this dot here, and you'll see that bend in the line. So when you see that bend where the line gets less steep here, right, it starts flattening out, I know that the object started to accelerate there, and it started to slow down in that one spot, okay? The other thing too, and I didn't write this down, but you'll also notice that when an object slows down, you can also look at how much longer the line gets from dot to dot, right? And that's because it's taking a lot longer for that object to move that same distance, okay? So that's another way you can kind of look at it too. But yeah, so you're just looking for you're looking for bends in the line. And anytime that there's a bend in the line, there's an acceleration that's happening. And in this case, it's a flattened line, right? Which means the object slowed down. Okay, so now we're going to put all this together. Okay, so what I need you to do is to just kind of set up your digital notebook, you need to, number one, take a screenshot of this graph. And then you're also going to need to take a screenshot of this, and you'll actually be typing in it. So you're going to have to create some text box and put them into each one as I do this. Okay, so as we mentioned earlier when we showed the other graphs, they were really, really super nice done and stuff, but that's not always the case of a motion, right? We're not always going to get an object that's going to be moving at a constant speed all the time. And also it's not going to be like speeding up or slowing down all the time. So this is something that happens quite a bit. So what we need to do is we need to look at each segment and saying, all right, did the object speed up, slow down? What happened to the slope from one dot to the next dot? So the first part, right, is we're going to look at it from 0 to 2 meters. So if I'm looking at it, right, distance is right here. So I'm looking at it from, the first thing is from this dot, right, and I'm going to circle it in red, to this dot, and say, what happened to the speed of the object from 0 to 2 meters? Now the beginning is the hardest because you're always trying to compare this part right here to what happened before. And since this just started, right, it's really difficult. So what I'm going to do is I'm just going to put a little line like this, right? And basically that line just tells you, hey, this part right here is what it was doing before, right? Before, like the negative time, it was doing nothing, right? It was just standing still the entire time. So what it did was it went from nothing, nothing, nothing to all of a sudden, boom, it moved up like this. So again, if we see this, we're looking at this dot right here. Do you notice that right here, there is a curve in the line, right? It's not straight, because if the object was continuing to do the same thing, we would see that this line would keep going straight across like this. And it doesn't. It curves upwards right here. So what does that graph look like? Doesn't that graph look like, say, this one right here, right? So when we look at it, hey, the object is speeding up. So when I come back here, we can write that the object is speeding up, right? Because remember, that graph changed here, okay? So now I'm going to look at it and say, what happened to the slope? Well, if an object sped up, right, that means that slope increased. All right, now let's look at the next one, which is from 2 to 4 meters. So now that I'm going to move my dot here, I'm going to go from 2 to 4 meters. Okay, I'm going to move this away. So now I'm looking at is what happened from this dot to this dot? What happened to the speed of the object? All right, now I'm going to bring in another line. And what this is, I call this the through line. And this tells me, it gives me an idea of whether or not there's a bend in the line. So if I match the slope of this to the very first one, you'll notice that, hey, if I were to go at a constant speed, and if I drew a straight line, this is what the line would look like, this dotted line. You'll clearly see that this line from here to here has bent downwards from the original slope of this line, right? So it flattened out. Doesn't that look just like this graph right here, the slowing down graph, where there's a bend in the line and it gets flatter, right? So now I know that the object slowed down. Right? And what happened to my slope? Right? Since it flattened out, the slope decreased. Right? It's less steep now. All right, now let's look at it from 4 to 6 meters. So now I'm looking at it from this dot to this dot. Okay, what happened here? So now what I'm going to do is I'm going to take my through line here and I'm going to match it up with the slope of that one. Right? And you'll see, right, as I'm going to do this, here we go. My through line, if you look at it, if I match it up right here with the slope here, look at it. That line continues to go on that exact same slope, that exact same line. Well, guess what? Isn't that graph look straight to you? So if I'm looking at it going, doesn't that look like this graph right here, right? Where it's a straight line. So when I look at it and I see my through line going through there, I know that it stayed at the constant speed. So I'm going to say constant speed, right? So there was no acceleration there. And my slope, since it stayed exactly the same, it stayed constant, right? So remember, if I'm looking at it from this dot to this dot, I'm always comparing it to what was happening before, and I'm drawing that through line. Okay, so now let's look at it from 6 to 8 meters. From here to, so this dot to this dot, right? So now what I need to do is I need to match it up again with my through line here. So I'm going to match it up with the line, the slope of the line here, and look at what happens to this line right here. If the line continued to go straight here, well, this line doesn't do that, right? What do you notice? It bends upwards again, right? This line gets more vertical. Well, isn't that exactly what happened at the very, very beginning, right? So I know that since this line gets steeper, I know that the object sped up, right? And my slope increased because the slope is now, right, steeper than what it was before. Okay, so that's how I'm using this dotted line as a through line to see where the bend in that point is. Okay, and that's how we would look at graphs as to knowing if something sped up, slowed down, right? If it had an acceleration and whatnot. All right, so now we're going to take that same exact graph that we had here, right? That we did in the previous slide right here. And we're now going to prove it, right? We can look at this part right here and say, okay, it sped up, it slowed down, and all that kind of stuff. But now we need to prove it. We need to prove that, yeah, it actually did speed up, slowed down, stayed constant, and sped up. And the way you do that is through math, right? And that's ultimately how cool math is that math predicts or math proves that science is right or actually science is wrong, right? So what we're going to do is we're going to calculate the speed of every single section, and we'll figure out whether or not actually something sped up, slowed down, or moved at a constant speed. Okay, so the first part we're going to look at is from 0 to 2 meters, right? Now, we're going to use the exact same equation that we used all of last week, right? Which is speed equals distance divided by time. So all that doesn't change this week, right? What we're doing is we're just going to look at speed now in little segments at a time. So all I want to do is look at it from this line or this dot to this dot, right? So I need to find the speed for that. So going back to my 3 steps, right? Anytime that we calculate speed, we always want to do these 3 steps. So from 0 to 2 meters, we need to figure out how much distance did the object move? Well, from here to this dot, we can look at it and say it went from 0 meters to 2 meters. So that's, right, 2 minus 0, which equals 0 meters. Okay? And I'm putting the math in here so you see how I got these numbers. Okay. Now the time, we can look at it and go, okay, so how much time did it take to go from this dot to this dot? Well, time is on the x-axis, so I'm going to look here. Well, it started at 0 and it ended at 2 seconds. So I know that it was 2 minus 0 seconds, which equals 2 seconds. Right? So now I've got my distance and I've got my time. I can now calculate speed. So I'm going to put in the equation here, s equals d divided by t. And now I'm going to plug in the numbers. S equals, and my distance is, right? Oh, I'm sorry, not 0. Jeez, it's 2. Right? It's 2 meters. So now my speed is 2 meters. Right? And I'm going to divide that by 2 seconds. Okay, so now if I do this correctly, right, I don't even need a calculator. I know 2 divided by 2 is 1. So I know that the speed of this object moved at 1 meter per second. Okay, so that's where we're going. And I know it's sped up from here to here because guess what? The object was staying still that first part. So I know it went from 0 meters per second to 1 meter per second. So I know I'm proven right that it sped up. Okay, all right, so now let's move on to the next part. So the next one is, right, moving from 2 meters to 4 meters, right? From this dot to now this dot. So let's look at it. We know that my speed is a question mark. Now my distance, right? Now it's going from 2 meters to 4 meters, right? So I'm looking at it going, okay, it went from 2 to 4, so I need to do some subtracting, right? It ended at 4 meters and it started at 2 meters, right? So I know that it traveled 2 meters. My time is from here to here. So again, right, my x-axis is right here. So I'm going to look at it and go, okay, it starts at 2 and it ends at 6 seconds. So I'm going to do a little subtracting, right? I'm going to do 6 minus 2. So I know that the object took 4 seconds to move from 4 meters or 2 meters to 4 meters. Now I'm going to plug in those numbers, right? So I'm going to go s equals 2 meters divided by 4 meters. And it's going to be s equals 0.5 meters per second. Oops, sorry, that should be seconds here. All right, now I know that we haven't had time to talk about this, but I always want numbers in decimal form because it's just going to be much easier to look at and to also graph. Right? Instead of, I know in math a lot of times you use fractions, but in science we actually use quite a bit decimal places. Okay. Now if you look at it, right, and we'll look at these a little bit later, but you can clearly see when we go from 1 meters per second to 0.5 meters per second, we can clearly see that it actually went down in speed. Right? It's half the speed that it used to be. Okay. All right. Let's do the next one. Right? S equals question mark. Now I'm going to look at it from 4 to 6 meters. So from this dot to this dot. All right, we're going to do the exact same thing. We're going to do some subtracting, right? So again, my distance is on this column. So if I look at it, this dot, it started at 6 meters, it went to 6 meters. And it started at 4 meters. So I'm going to do 6 minus 4 because that's how many meters it traveled from 6 to 4 to 6. All right. Now, how much time did it take to go from here to here? Well, when I look at it, it went from 6 seconds to 10 seconds. So I'm going to do 10 minus 6, right, which is 4 seconds. Okay, so I'm going to plug in those numbers again. S equals, my distance is 2 meters divided by 4 seconds. Okay, so when I do the math, S equals 0.5 meters per second. And I'm going to highlight it because I love highlighting because it tells me what the answer is right away, just visually. Right, and again, now you look at it and go, okay, I can see that from 2 to 4 meters and from 4 to 6 meters, it stayed at a constant speed. The math proves that. Okay, and then let's do the last one, which is from 6 to 8. So from this dot to that dot right there. So I'm going to put a question mark, right, because we're always calculating speed. So let's look at distance. It's going from 6, right? So if I look all the way across here, 6 to 8 meters. So I'm going to go 8 minus 6 because that's how many meters it traveled. So it's really the difference is 2 meters. And then I'm going to look at it and go, okay, from 10 to 12 seconds, right? Now if I'm looking for time. So I'm going to do 12 minus 10 seconds equals 2 seconds. Right? So now I'm going to plug in the numbers again and go S equals 2 meters divided by 2 seconds, because s equals d divided by t. And I get s equals 1 meter per second, right? So now we're looking at it. Based on the math, it looks like it goes, hey, it started at 0. If it sped up to 1 meter per second, then it slowed down here. And then from here to here, it stayed the same speed. And then it looks like it went from this to getting faster. So it went speed up, slow down, constant speed, speed up. Well, isn't that what we got here? It went speed up, slow down, constant speed, speeding up. Okay, so now when I look at this graph and how I did it qualitatively, just looking at it and doing the math, my math proves that my object did exactly what it did. All right, and that's how you use the speed equation to prove when you look at a graph what's going on. And that's what we're doing this week in our labs. All right, and that's it. So what you need to do now is obviously screenshot, right, the graph, and you need to make sure that this table right here gets into your notes, and you're done.